The first window we're going to look at is the raised cosine window, also known as the Hahn or Hanning window. And it's given by this formula here with this cosine. We have this 2 pi divided by L and this factor of 0.5 here. So we can see for L equals to 16, we have this is an example of the raised cosine window. And we have here the equation exactly like defined here. So we observe that the center is in between two samples. We can obtain its frequency response with frac c. This time we're going to define a function just to plot automatically the frequency response, because we're going to analyze the frequency response of many different windows, so we don't need to write this all the time. So it's the same, we use signal, pi signal frac c, we have our normalized frequency, we calculate our magnitude in dB with 20 times log 10. In this case here we're just adding this small number to avoid the log of 0. Then we are having these two plots, one for the magnitude in dB and one for the phase in degrees. So here is the frequency response for the raised cosine window with even length. So this time L is equal to 16. Here we can see that we will obtain a much higher attenuation in comparison to the rectangular function. For the first side lobe at more or less minus 35 dB, measured from the maximum of the main lobe, so it's the pass band, and far off in the stop band we get about minus 60 dB, so it's far off the stop band, but at the cost of a wider main lobe. So it's 3 dB is at about 0.1 pi, and that's twice as wide as for the rectangular window, which leads to a wider transition band. So we have a wider main lobe, a wider transition band. So this shows that there's a general trade-off. We can trade transition width for stop band attenuation. For odd window lengths, we have here this formula here, and we know there's a difference here. It's 2 pi divided by L, and here we have 2 pi divided by L minus 1. So for 17 samples, so the number of samples of the impulse response equal to the coefficient, so this represents an FIR filter. So we have now here our equation just as given here, and here we have our impulse response of our filter, and here the center is right on the sample. So when we compare to the even, the center is in between two samples, and here the center is just right on one sample. So another window, it's not a raised cosine window, but we also have the sine window. It's widely used. And the equation for the sine window is given by these functions here. We have this for even lengths or for odd lengths. We have here this difference here. An example for even length, where L is equal to 16, using the sine window, is given by this plot here. And we notice is quite different from the raised cosine. We have here this shape, and with the sine we have this shape here, and the frequency response is given by this plot here. And here we can see that the main lobe is somewhat narrower than when compared to the raised cosine, with a 3 dB width of about 0.04 pi, but the first side lobe has only minus 20 dB attenuation. But the further side lobes increase in attenuation. So this attenuation is more than when compared to the rectangular window, but less than for the raised cosine. On the other hand, its transition bandwidth is less than for the raised cosine window. So we always have this trade-off of the transition bandwidth and stop band attenuation. Observe that this always results in positive values for the window functions and that they are perfectly symmetric. For odd lengths, there is a sample right at the center, and for even lengths, the center is right between two center samples.